Hello my dear students, welcome you to this lecture 3 of KTG. Today we are going to discuss many concepts, that is we will discuss about kinetic theory of ideal gas, then we will discuss different speed of gas molecules, then Maxwell-Boltzmann distribution curve, then we will discuss about pressure of an ideal gas as well as the kinetic interpretation of temperature. Okay, so these are the things that we are going to discuss in this lecture. So without wasting much time, let's move on to the concept, that is the first one, which is kinetic theory of ideal gas. Here we are discussing many assumptions which are included in the kinetic theory of ideal gas. As you can see here, a diagram, right? There is a diagram. Okay, from this diagram itself we can tell many assumptions. The first one is, what about the shape and size of these gas molecules? Yes, these gas molecules are considered to be spherical in shape. They are point masses, they are spherical in shape. Okay, so that is the first one. A gas consists of very large number of molecules which are perfect elastic spheres. Okay, and these gas molecules are moving randomly in a very high speed. Okay, random motion means they are moving to different directions. There is no particular direction. Okay, they are moving to different direction in a very high speed. Okay, so that's the next one. Molecules of a gas are in constant random motion. And now think of it, you are taking gas in a container, you are taking ideal gas in a container. Okay, and these gas molecules are randomly moving here and there. Then what is going to happen? Yes, they will collide each other, right? These gas molecules will collide each other, as well as they collide with the walls of this container. Okay, walls of this container. Then these collisions are considered to be elastic collisions. Okay, what is mean by elastic collision? Elastic collision you have learned in work energy power, right? Elastic collision means both the kinetic energy and the momentum are conserved. That is, kinetic energy before collision will be equal to kinetic energy after collision. Momentum before collision is equal to momentum after collision. So the collision of these gas molecules are considered to be elastic. That is the third assumption. Okay, now size of this molecule. Okay, size of this molecule is negligible compared to the distance between the molecules. As you know that in solids the gas molecules are very closely packed, right? When you come to liquids, there will be comparatively some more distance between the molecules, gas molecules. When you come to gas, okay, these gas molecules have more distance in between them compared to solids and liquids. So hence, compared to the average distance between these gas molecules, we can neglect the size of the molecule. That is what I told in the first part, that is, the gas molecules are considered to be point masses. Clear? Okay. Now the next assumption is, we don't consider or we neglect the interaction, that is the attractive or repulsive force between the gas molecule. Do you remember in lecture 1 we have discussed about van der Waals equation. There we consider the pressure correction because we are considering the force of interaction between molecules. That is for real gases. For ideal gases, we consider there is no attractive or repulsive force, as well as we does not consider the gravitational force of attraction. Since these gas molecules are having very less mass as well as very high speed. Okay. Now, the density of gas is constant at all points in a container. Okay, the density of gas remains same at every point in the container. So, these are the important assumptions related to kinetic theory of ideal gas. I hope you understand these points, right? Okay. Now, let's learn about the different speeds of gas molecules. Okay, as we have discussed, the gas molecules are in random motion and these molecules are moving with different speeds. Okay, usually we consider three different types of speeds, that is RMS speed, root mean square speed, then we consider most probable speed, then average speed. Okay, so what is root mean square speed? Okay, before entering into the root mean square speed, let me ask you something. Why do we need a root mean square speed? Why it is RMS speed? We have other speeds like average speed, then the most probable speed. Then what is the need of this root mean square speed? It is because, first we will understand that, okay, then we will get into the equation of root mean square speed. Okay, suppose I ask you a question. There is a container, okay, there is a container, and in this container you have many molecules, isn't it? Suppose if the first molecule is having a speed v1, the next one have v2, the other one is v3, then v4, like that. You are considering 4 molecules, suppose. Then how will you calculate the average kinetic energy? Suppose if the first molecule is moving with v1, then the kinetic energy will be k1. For the next one, the kinetic energy will be k2. For third one, it will be k3. Fourth one, it will be k4, isn't it? So the kinetic energy is different for different molecule. So what we will do? We will calculate the average kinetic energy, isn't it? Am I right? We will calculate the average kinetic energy. Okay. So what will be your average kinetic energy? You will calculate it as half m v average square, isn't it? You may be thinking like this. We will calculate the average speed, then we will take the square of it, multiply with half m, so that we will get the average kinetic energy. But when we calculated it experimentally, we didn't get the correct average kinetic energy. Okay, so that it is half m. We want to consider some speed here, okay, square of some speed here, but it is not average speed. Okay, it is not average speed. It is actually VRMS. Okay, it is actually the VRMS. So what is the basic concept behind the root mean square speed? It is that speed of the molecules that will give you the average kinetic energy upon calculation. You get the idea? I hope you get the idea. Okay. Now, by understanding this, let's talk about root mean square speed. You can define it as the name itself, that is, it is the square root of mean of squares of the speed of different gas molecules. Okay, how to write it? VRMS is equal to, okay, listen, square root of, you take a square root, mean of, how you take the mean? Mean means if you have three quantities, then you add the 3 quantity divided by 3. If there are 4 quantity, add 4 quantity divided by 4, right? If you have n, then divide it with n, right? So let's consider n molecules with different speed. So we will divide it with capital N. Okay. Then square of the speed, which means v1 square plus v2 square plus v3 square plus etc. plus vn square. Clear? Yes. So this is what is mean by root mean square speed. Okay. Now it can be even written as root of v bar square. Okay, root of v bar square. Okay, where v bar square means it is the mean square speed. Mean square speed. Okay, you take the root of mean square speed, you get VRMS. Okay, now for doing problems, we will be using the equation like VRMS is equal to root of 3 kBT by small m, or which is even equal to root of 3 RT by capital M, or even it is equal to root of 3P by rho. Okay, these equations are important. From this, the most used equation is root of 3RT by capital M. Now what is the difference between this small m and capital M? Okay, let's understand that. Small m means it is the mass of each molecule. Okay, it is the mass of each molecule. Whereas capital M means it is the molecular mass. Molecular mass. Okay. So how to calculate the small m? The small m is calculated as molecular mass divided by Avogadro number, that is Na. Okay, Avogadro number, that is Na. So these are the things that you need to remember regarding root mean square speed. Okay, now the next one is average speed. Okay, what is average? In mathematics also, average means you add the observations divided by total number of observation, isn't it? That is the same concept here. Okay, you add the different speed of the gas molecules divided by total number of gas molecule. Okay, so it is the arithmetic mean of speed of molecules in a gas at a given temperature. Is that clear? Okay. So we can write V average is equal to V1 plus V2 plus V3 plus etc. plus Vn divided by capital N. This is the average speed. Okay. Now the other equation for calculating the average speed is root of 8 kBT by pi small m. Okay, kb, you know what is kb, right? It's Boltzmann constant. T is temperature, pi is 3.14, small m is mass of each molecule. It is equal to root of 8 RT by pi capital M. Okay, R is universal gas constant, T is temperature, capital M is molecular mass. Okay, pi is again 3.14, you know that. Then it is again equal to square root of 8 P by pi rho. Okay, where P is the pressure of the gas and rho is the density. Okay, so this is the next set of equations that you need to know. Here also the most important is this one. Okay, root of 8RT by pi m. Now let's discuss what is most probable speed. Most probable speed means it is the speed which is possessed by most number of molecules. Okay, suppose you consider there is a gas which consists of 20 molecules. It's just an example, okay, which consists of 20 molecules. And out of these 20 molecules, the speed possessed by most of the molecule, that is considered to be the most probable speed. Suppose if 16 of those molecules have a speed like 25 meter per second. You think of it. Okay, it's just an example. Okay, 25 meter per second. Then, since 16 molecules have 25 meter per second, you will consider your most probable speed to be 25 meter per second. You get the idea? That is what is the meaning of most probable speed. Okay, so we can tell that it is the speed possessed by maximum fraction of the total number of molecules. Okay, now what is the equation for finding the most probable speed? VMP, that is most probable, okay, is equal to root of 2 kBt by small m, which is also equal to root of 2 RT by capital M, or which is again equal to root of 2p by rho. Okay, so these are the concept of different types of speed of gas molecules. Okay, now related to this, okay, related to this, we have something called as Maxwell-Boltzmann distribution curve. Okay, now it is a very simple concept, that is, we are considering the fraction of particles possessing a specific speed on the y-axis, okay, and speed is considered on the x-axis. Okay, if we plot the graph between these, then the graph will be of this shape. Okay, you don't have to know how we get this curve, okay, because it is based on a mathematics part that you don't have to learn. Okay, there is an equation. Based on that equation, we have got this shape of a curve. You don't have to learn that equation and all. You just have to remember the nature of this curve. Okay, it is of something like this. Okay, and out of this, we know the speed possessed by the maximum fraction of molecule is called as most probable speed, isn't it? So here, the speed corresponding to this peak is considered to be the most probable speed. Okay, it is Vp or Vmp, whatever it may be. So this is corresponding, this value of speed corresponding to the most probable speed. Clear? Now, this line, it represents the average speed. Okay, V average. Okay, then again moving down this curve, at this part we consider the root mean square speed. Okay, this is the part of the curve that is corresponding to root mean square speed. Okay, VRMS. Clear? So this is what you have to understand about this Maxwell-Boltzmann distribution curve. And from this curve, you can also understand that your VRMS is greater than, V average is greater than VMP, isn't it? Okay, so this is also an important point. Okay, now if you are considering the effect of temperature on this distribution, okay, you are considering the effect of temperature on this distribution, then the first one, okay, the first one represents the curve at a temperature T1. Now, if you change the temperature to T2, that is, if you increase the temperature to T2, then the curve become like this. Okay, here your T2 is greater than T1. Okay, so what you have to understand now, for this first temperature T1, this will be your VMP1, right? Most probable speed corresponding to the first curve. Now, this will be the most probable speed corresponding to the second curve, right? Now, out of it, which is greater? Which is greater? VMP2 is greater than VMP1, isn't it? Which means that if you increase the temperature, okay, if you increase the temperature, then your speed will increase. Average speed of the gas molecules will increase. Not only this most probable speed, the average speed will increase, most probable speed will increase, the root mean square speed will increase. All those speed will increase as you are increasing the temperature, and this curve will shift like this, as you can see in the figure. Is that clear? So these are the things that you need to know about Boltzmann distribution curve. Okay, you don't have to learn those equations and learn how we obtain this shape of a curve. You don't want to know those things. Okay, now let's derive the formula for pressure of an ideal gas. Okay, as we have discussed, the molecules in a gas is in random motion, isn't it? So during their motion, they collide each other as well as they collide with the walls of the container. Hence, they will exert a pressure, isn't it? So we are supposed to calculate or derive an equation for the pressure exerted by these gas molecules. Okay. And it is very important to remember this derivation for both board exam as well as competitive exam. Because in competitive examinations also, there are numerical problems that we have to do in the way we derive this equation. Okay, there are questions in which you have to use the final equation from this derivation. Also, there are questions that have to be done in the way you are deriving it. Okay, so first of all, we need to take ideal gas in a container, isn't it? So here is a container which is a cube of length, say L. Okay, so we can write, consider ideal gas in a container of volume V. Okay, so let the volume of the cube be V. Okay, now we need to calculate the pressure, isn't it? So what will be the basic logic? Think of it. You know that pressure is equal to force by area. You have learned in fluids. So the basic idea is you want to calculate the force, you want to calculate the area and divide them so you get the pressure. Is that okay? Okay. So for getting force, let's consider a single molecule in this gas. Okay, let's consider a single molecule here. Single molecule here. Okay, then the velocity of this molecule can be marked as, okay, let it be x, let it be y axis, let it be z axis. Okay, then it can be marked as vx comma vy comma vz, isn't it? That is the velocity of the molecule along x, y, z. And now, if this molecule is moving along the x direction, okay, and then it collides with this wall. Okay, this molecule is moving along x direction and it collides with this wall of this cube. Then what will happen? Yes, it will bounce back, isn't it? So it will bounce back. Okay, so it will bounce back. Then what will be the velocity? The velocity can be marked as minus vx, vy, vz, isn't it? Why minus Vx? Why we have minus Vx? It is because, see, it was initially moving along positive x direction, isn't it? It collide with this wall, then it get reflect back, which means now it is moving along the negative x direction. Velocity is a vector quantity, so it will become minus Vx. Okay, and since it is moving along x direction, okay, and it get reflected along the negative x direction, there won't be change in the y component, isn't it? So Vy and Vz will remain as such. Is these things are clear to you? Okay, so let's go ahead. Now here I have marked different parameters like impulse, change in time, force exerted by single molecule. Okay, these are some safe landing points during the derivation. It is important to remember the formulas in each of these things. Okay, you will have to use that in problems. So first we will calculate the impulse. Okay, first we will calculate the impulse. What is impulse? We know that the impulse is equal to change in momentum, isn't it? Then it is equal to mv minus mu, where mv is the final momentum, mu is the initial momentum. Then upon substituting, we can write it will be m. What about the final velocity? The final velocity was minus Vx, isn't it? Then why don't we consider Vy and Vz? As you know, along y direction and z direction, there was no change in the velocity. If there is no change in velocity, there won't be change in momentum. So there will not be impulse. So the impulse is along the x direction. So that is final velocity is minus Vx. Okay, minus m into what is initial? Initial velocity is Vx. So that your impulse equation is minus 2mvx. Okay, so this is an important equation. Now what about the change in time? We know that speed is equal to distance by time. So that time is equal to distance by speed. So the change in time can be marked as distance by speed, isn't it? So delta t is equal to, what about the distance? Okay, let's see. What is the distance? This molecule is starting from this end. Then it moves along x direction. So the distance covered will be the length of the cube L. Then it get reflected from this wall and again travel along x direction. Okay, so again it will cover a distance L. So from here it moves, it become L. Now it come back again L. So the total distance is 2L, isn't it? So the total distance is 2L. Okay, it was capital letter L, right? Length of the cube was marked as capital letter L. 2L by speed. What is the speed? Speed is Vx, isn't it? Okay, so this is the equation. Now what is the force exerted by a single molecule? That is, what is the force exerted by this molecule? Okay, we know impulse is nothing but force into change in time, right? Force multiplied by time, which is equal to minus 2mvx. That minus shows the direction, right? We neglect that negative because we need the magnitude. Okay, so that is 2mvx. Now what about delta t? So it is force into delta t is 2L by Vx, which is equal to 2mvx. Okay, so that your force is 2mvx by 2mvx. You will take this Vx to the right side so that it becomes into Vx by 2L. Okay, now cut the common term. You cut this 2 and this 2, so that your force, let's mark this as Fx. Okay, because it is the force given by a molecule that is moving along x. So Fx is equal to m Vx square by L. This is the equation. Okay, this is the equation for force exerted by a single molecule. Okay, so now we are calculating the force exerted by n molecules. Then what will be that force? That force Fx will be equal to capital N times, what was the previous equation? mVx square by L, isn't it? Here this Vx is the velocity of a single molecule, isn't it? If we are considering n molecules, then will every molecule have same velocity along x? No. If one molecule is having v1 velocity along x, the other molecule will have v2 velocity along x, other molecule will have v3 velocity along x. So what will you do? You will take the average of those, isn't it? So it will be n into m by L Vx1 square plus Vx2 square plus etc. plus Vxn square whole divided by n. Is it? So this can be written as nm Vx bar square by L. Am I right? Where your Vx bar square is mean square speed. Do you agree? It is okay, mean square speed along x. Clear? Now we need to calculate the pressure. Okay, we need to calculate the pressure. How to calculate the pressure? Yes, the pressure along x will be force along x by the area, isn't it? That is, what about the force? That is nm Vx bar square divided by L whole divided by, what about the area? That is what we want to calculate. Area is, this is the area we are considering, because every molecule will come and collide at this wall. So what about the area of this wall? Area will be L square, since it is a square, isn't it? Okay, so divided by L square. So this will become nm Vx bar square by L cube, which is equal to nm Vx bar square by L cube is the volume. Initially we have taken a condition, consider an ideal gas taken in a container of volume capital V. So this will be capital V, isn't it? Now is our derivation completed? No, never. Why? Because it is the pressure considering the velocity along x. Okay, so we need the total pressure on every wall, right? Total pressure of these gas molecules. So how to get that? Now the gas molecule will have velocity along x. Similarly, there will be gas molecules which is moving along y. There will be gas molecules which are moving along z. Okay. So what will be the resultant velocity? Velocity is basically vector quantity. How can you find the resultant? Since these vectors are perpendicular to each other, okay, you can write your resultant v bar square will be vx bar square plus vy bar square plus vz bar square. Do you agree? Now vx is equal to vx bar square will be equal to vy bar square is equal to vz bar square. Why they are equal? Because we consider that gas have isotropic nature. What is isotropic nature? You have learned in chemistry that isotropic nature means the property of gas will be same in every direction. Okay, so the speed should be same. Okay, the mean square speed along every direction should be same. Therefore, we can write v bar square as 3 times that of vx bar square, isn't it? So that your vx bar square is equal to 1 by 3 of your v bar square. Okay, so that your pressure becomes P is equal to 1 by 3 n m by v bar x. Sorry, you are replacing this v bar x square, right? So that will become v bar square. Okay, now what about this capital N by V? That is number of molecules in a unit volume, isn't it? That can be taken as small letter n, which is called as number density. Okay, also when we learned about root mean square speed, okay, we'll go to that part. Yes, this was root mean square speed. Do you remember this result? So from there you can write your Vrms square is equal to the V bar square, isn't it? Okay, therefore your final equation of pressure is 1 by 3, N by V is small n, this is M Vrms square, okay, Vrms square. So this is the final equation for pressure. I hope you understand this. Now let's see the relation between pressure and kinetic energy. Okay, so what is the equation of pressure? The equation of pressure is 1 by 3. I'm considering this one. Okay, instead of this V bar square, I will be writing Vrms square. Okay, the rest of the things are same. 1 by 3 capital N M by V. Okay, so 1 by 3 capital N M Vrms square by capital V, isn't it? Now N is number of molecules and small m is mass of a single molecule. So N into M will be the total mass of the molecule. Okay, M into N will be the total mass of the molecule capital M. Okay, so this can be written as 1 by 3 M by V into Vrms square. Okay, now what is mass by volume? Mass by volume is density, isn't it? So that becomes the density of the gas. So pressure is equal to 1 by 3 rho Vrms square, isn't it? So this is your equation number 1. Okay, now we are deriving the relation between pressure and kinetic energy. Okay, so now let's see what is kinetic energy. We know that the kinetic energy per unit volume. Okay, per unit volume, the kinetic energy E is equal to half m by v Vrms square, isn't it? Because kinetic energy is half mv square. Okay, so that m divided by v, because we are considering kinetic energy per unit volume. Okay, okay, so that this becomes kinetic energy is equal to half rho Vrms square. Mass by volume is density, isn't it? So that your rho into Vrms square is 2 times the kinetic energy per unit volume. Question number 2. Now put 2 in 1 so that your pressure is equal to 1 by 3 multiplied with, instead of this rho Vrms square, you substitute 2e, so that it becomes 2 by 3 times that of the kinetic energy per unit volume. Okay, hence we can tell that in your notebook you have to write that the pressure is numerically equal to 2 by 3 of kinetic energy due to translational motion per unit volume. Okay, because you are considering the translational motion of the molecule, the straight line motions of the molecule, isn't it? You are not considering vibration or rotation. Okay, hence you can tell that the pressure is numerically equal to 2 by 3 of average kinetic energy, or 2 by 3 of kinetic energy due to translation per unit volume. So that is what you have to note about the relationship between pressure and kinetic energy. Okay, now let's go to the last and final topic, that is kinetic interpretation of temperature. Okay, we will start from the same equation of pressure. We know pressure is equal to 1 by 3 Nm by V into Vrms square, isn't it? Now we can write this as PV. Let's take this volume to the left side. So PV is equal to 1 by 3 Nm Vrms square, isn't it? Can I write it as, listen carefully, okay, 2 by 3 N into half M Vrms square. Can I write it like this? Yes? Is there any mistake? No. Why? Why? Because if you cut this 2 and this 2, then this equation will be similar to the above equation. There is no change. Okay. Then what about this half m Vrms square? Half m Vrms square is the kinetic energy of that molecule, right? Of that single molecule. So that your pressure into volume becomes 2 by 3 N into kinetic energy, isn't it? Equation number 1. PV is equal to NKBT, isn't it? So let's call it as equation number 2. Your 1 and 2 are same. Okay, so 1 is equal to 2, so that you can write 2 by 3 NKE is equal to NKBT. Let's cut the common terms, N, isn't it? So that your kinetic energy equation, kinetic energy equation becomes you take this 3 to the right side, 2 also to the right side. So it is 3 by 2 kBT, right? Yes. So your kinetic energy equation is 3 by 2 times kBT. Okay, from this we can conclude that average kinetic energy of a gas molecule is proportional to the absolute temperature. Why? Because here 3 by 2 is a constant, Kb is also a constant, so that kinetic energy is proportional to temperature, right? So kinetic energy is proportional to the absolute temperature, which means that kinetic energy of ideal gas does not depend on any other factors like pressure, volume or anything. Okay, it only depends on temperature. Clear? So that is what is the meaning of kinetic interpretation of temperature. So I hope you understood every topics that we have discussed in this lecture. If you have any doubts, let me know in the comment section. And also, if you like the video, you share it to your friends. Okay. So see you all in more upcoming lectures. Stay tuned with EDIFIWAY Infinity. Bye bye.